Let's talk about a few things we've learned about vector spaces. We said that if V is a vector space, and W is a set of vectors that belong to the vector space, then we say that V is equal to the span of W if for all vectors X and V, we have X is equal to C1V1 plus C2V2 all the way to CKVK for some C1, C2 to CK scalars. So in other words, we can write X as a linear combination of the vectors in W. We said that the vectors in W are linearly independent. So V1, V2, all the way to VK are linearly independent if there exists D1, D2, all the way to DK, VK. If this is equal to 0, if and only if this D1 is equal to D2, which is equal to DK, is equal to 0. So we can't write any of these vectors in W as a linear combination of the other vectors in W. Here's a question for you. For the vector space Rn, is there a minimum or a maximum number of vectors that can span V? Well, this V is actually Rn, so V is equal to Rn. And the answer is there's a minimum, but not a maximum. Let's see this with the vector space V is equal to R3. So remember that vectors in V look like A, B, C. So V is all the vectors A, B, C, where A, B, and C are real numbers. Well, in order for us to get 3 different numbers here that don't depend on each other, we're going to need at least 3 vectors. Let's say the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. This will give me A, B, C. Now, of course, we can find 3 other vectors that will give us A, B, and C, but this is the easiest example of 3 vectors. So it's going to take at least 3 vectors because we need 3 numbers here that don't depend on each other. And if we only had 1 vector, then the most letters we could get is just one of these. So like if we just used 1, 1, 1, well, there's no way I can get something like 4, 5, 6. If I multiply it by 4, I'll only get this one being the top one, which here I have as A. So in order for me to get these 2 numbers here that don't depend on this first one, I need at least 3 vectors. Now I can have more than 3 vectors that span V. So let me show you. So we said that one spanning set is 1, 0, 0, 0, 1, 0, and 0, 0, 1. I'm going to give you another spanning set. I'm going to repeat all of these vectors, and then I'm going to add another one. Let's say, shouldn't be a plus here, should be a comma. Let's say the vector 1, 4, 9. This is also a spanning set for our vector space. Why is that? Well, notice that we can write the vector ABC, which belongs to R3, in the following way. ABC is equal to A times 1, 0, 0, plus B times 0, 1, 0, plus C, 0, 0, 1, plus 0, 1, 4, 9. That's one way to do it. I'm sure there's another way to do it as well. You could probably put a 1 here and figure out what A, B, and C would have to be, or rather this should be maybe alpha 1, alpha 2, alpha 3, and see what they have to equal in terms of A, B, and C. But you can add as many vectors as you want. You can add any linear combination of these three vectors. You can add it and the vectors will still span. I could copy this one. I could put 2, 8, 18. I could put 1, 1, 1. I would just have to put zeros in front of them. And remember, for a set to span our vector space, we just have to be able to put in front of those vectors a scalar and have the sum of all of those vectors equal any vector in that vector space. So these span. So there is not a minimum number, there is a minimum number but not a maximum number of vectors that can span Rn. So for Rn, here we just used R3. For Rn, we need n vectors to span Rn. So we need at least n vectors. So let's even put that here. Now we can't choose any n vectors. We have to be careful. We can't say, for example, let me erase this. For example, V is not equal to the span of 1, 0, 0, 0, 1, 0, 2, 4, 0. Here I have three vectors, but they don't span this vector space. Why? Because in order to get A, B, C, and C not being equal to 0, I don't have anything other than 0 here. So there's no way I'm going to get this number here. So we have to be careful with the vectors we choose, but we need at least 3 of them for V is R3, and we need n of them for V is equal to Rn. For the vector space Rn, is there a minimum or maximum number of vectors that are linearly independent? And the answer is yes for maximum. So there is a maximum number of linearly independent vectors, but not a minimum number. let's look at the case v is equal to R3 again. The vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 are linearly independent. And this is obvious, right? Because look, there's no way that you can get this vector from these two because they don't have anything written here in this third entry. And you can't get this one from these two, and you can't get this one from these two. So they're going to be linearly independent. But this is the maximum number, because if I choose any other vector in R3, anything you want, we could say 1, 1, 1. Well, this 1, 1, 1, because these vectors span, this vector is going to be a linear combination of these. Notice that 1, 1, 1 is 1 times 1, 0, 0, 1 times 0, 1, 0, plus 1 times 0, 0, 1. And if I move this vector to the other side, so I get negative 1, 1, 1, 0, 1, 1, 1 is equal to this, plus this. Well, this is going to be equal to 0, 0, 0. And you can see that we have scalars that are not all 0 that give us the 0 vector. So they're not linearly independent. Now again, you have a maximum number of linearly independent vectors, but you have to be careful with which vectors you choose. And you don't have a minimum. So for example, we said that these vectors are linearly independent, but if I delete one of them, these are still linearly independent. And if I delete another one, this is linearly independent. So if we have a linearly independent set of 3 vectors, then taking any one of those out will give us a linearly independent set. But you can't do something like 1, 0, 0, 2, 0, 0. Here we have 2 vectors, but they're not linearly independent. You have to be careful on what you choose. So, for Rn, you can have a maximum number of n linearly independent vectors. So for Rn, we can have a minimum number of n vectors that span and a maximum number of n vectors that are linearly independent. This number n corresponds to what we call the dimension of our vector space. And this set of vectors, if we can show this, we have a set of vectors, n of them, that are linearly independent and they span, then we call that set a basis. And this is the beginning of section 3.4. So if we have a vector space V and n vectors from that vector space, we say that these n vectors form a basis for that vector space if and only if all of the vectors are linearly independent and all of the vectors span our vector space. This is a really important definition. Make sure you write it down and memorize it. So this is a good way to think of a basis. A basis is the minimum number of vectors that span and the maximum number of vectors that are linearly independent. So for R3, a basis for R3 and usually we denote a basis with the letter B, is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is actually called the standard basis for R3. Sometimes people denote it as E1, E2, and E3. This is a basis because, so we can say that B is a basis. Oops. B is a basis since R3 is the span of B and all the vectors in B are linearly independent. Now, a vector space has infinitely many bases. I'm going to say for the plural word, so one, if we only have one basis, we call it a basis. If we have more than one basis, we call it bases, because this is basis too, and I don't want to say the same word, but we're going to call more than one bases. And every vector space can have more than one basis. So let's show that for R3, this is also a basis. So what do we need to show? Well, we have to show that these vectors are linearly independent and they span R3. Now, one of those is actually easier than the other to show. Showing that vectors are linearly independent is easier than showing that they span. So let's start with linearly independent. So let's call this the set of vectors. Let's call it B hat. And I want to show B hat is a basis. So the first thing I'm going to show is that the set of vectors is linearly independent. So I'm going to multiply each one of these vectors by a scalar. And set it equal to 0. And now I want to figure out if the only solution to this, for the C1, C2, and C3, is 0, 0, 0. All right, there's several ways to do this. We've learned them. We're going to make an augmented matrix and put that augmented matrix in reduced row echelon form. If the reduced row echelon form is the identity matrix, then the only solution is 0, 0, 0. You could also take the determinant of this. If the determinant is non-zero, then it's invertible, which means the reduced row echelon form is the identity, which means there's only one solution. So I'm just going to subtract row 1 from row 2. And then I'm going to get rid of this 2 here. So I'm going to multiply this by a -2. I think this becomes 1. And I really don't have to go any further because I can see that I can put this in reduced row echelon form and that the reduced row echelon form is the identity. So then this implies C1 is C2 is C3 is 0. And these vectors are linearly independent. Now we need to show that these vectors span our vector space R3. Okay. I always don't put enough space. So let's move this down. Okay. So let me copy these vectors. Okay, so I want to show they span R3. So show B hat, which is equal to this, spans R3. So I want to show that for any vector A, B, C, it can be written as a linear combination of these three vectors. Again, this is the same thing as what we did before. We're going to make an augmented matrix. The only difference is we put A, B, C here. So 1, 1, 0, 0, 1, 2, 1, 0, negative 1, A, B, C. And if there's a solution, what's going to happen is that you're going to get the identity matrix for the reduced row echelon form, and you're going to get some kind of, you're going to figure out like what A, B, and C are. Sorry, you're going to figure out what alpha 1, alpha 2, and alpha 3 are. And you're going to get that on this side. I'm going to actually do all of that, but I wanted to also mention to you that if these three were not going to give you a linear combination that equals A, B, C, then you would get a row of zeros. And if you get a row of zeros and then you have something that's non-zero right here, then it's an inconsistent system. So that's the only time that the vectors will not span. But as we know, we've already seen this matrix, when we put it in reduced row echelon form, we're going to get the identity matrix. So we're going to get a solution. We're actually going to figure out what alpha 1, alpha 2, and alpha 3 are because I think it's a good exercise. But you don't have to go this far. It's obvious from this piece that you can find alpha 1, alpha 2, and alpha 3 because this part reduces to the identity matrix. But let's do this anyway. So again, I'm going to take negative row 1 and add it to row 2. I get 1, 0, 1, A, 0, 1, negative 1. I usually mess this up, so I'm going to make sure I don't mess it up this time. So this 0, 1, negative 1, and this is B minus A. And then we have 0 to negative 1C. And I'm going to get rid of this 2. And how I'm going to do that is I'm going to multiply row 2 by a negative 2, add it to row 3. So I'm going to cross this out, and I'm actually going to put it on the top. 0, negative 2, positive 2, and then negative 2b plus 2a, because we're multiplying by a negative, and then multiplying by 2. Okay, so we get 0, 0, 1, c minus 2b plus 2a. And the last step is to add this row to this one, and then multiply this one by negative 1 and add it to this row. Okay, so our final step, 1, 0, 0, 0, 1, 0, 0, 0, 1. We get A minus C plus 2B minus 2A. And then B minus A plus C minus 2B plus 2A. And then C minus 2B plus 2A. And just simplify this stuff. And you'll see that you'll figure out what alpha 1, alpha 2, and alpha 3 are in terms of A, B, and C. So when you simplify this, alpha 1 is negative A minus C plus 2B. Alpha 2 is A minus B plus C. And then alpha 3 is C minus 2B plus 2A, as long as I didn't make some silly mistake here. What does this tell you? So you can put all of that stuff here. And any A, B, and C you choose, so let's say we chose 1, 1, 1. Then we can plug in 1, 1, 1 into this, and then we'll figure out what we need to put for each one of these. You should try it. So choose some vector, maybe like 5, -3, 8, and then plug those in for A, B, and C here. See what you get here, put those numbers here, and then add these vectors together to make sure you get this. I think I said 5, -2, 8. Great. So that was a lot of work, as you can see, but we've shown that these vectors span R3. So the vectors span R3, and they're also linearly independent, which means they're a basis for R3, and that's what we wanted to show. So these vectors are a basis for R3. Okay, let's move on. I also want to tell you something that we're going to see in a few minutes. We really only have to show that these vectors are linearly independent. We don't actually have to show that the vectors span R3. We're going to see that as long as we have the right number of vectors, if we know the dimension of the vector space, which is the number of vectors in a basis, we only have to show that they're linearly independent. We get spanning for free.